This video includes information on Ksp and precipitates.
Let's look at how we can use Ksp to decide whether or not we're going to form a precipitate in a solution. And precipitates form when there are too many ions present in the solution that can actually be dissolved in the solution. And the excess ions would stick together and precipitate on the bottom of your container. Okay, so in chapter 5, way back in Chem 1, you learned about basic solubility rules. And those applied to solutions that are fairly concentrated, 0.1 molar or higher. But now we're dealing with really low concentrations. The numbers we've been dealing with have very small exponents. So what we're going to do is we're going to calculate Q values, similar to the way we did in equilibrium problems in previous chapters. And we're going to compare the Q values to the K values to decide whether or not we have an equilibrium established. And if we don't, we can figure out whether a precipitate forms. When we go to calculate our Q value, our ion product, it's calculated the same way that the K value is calculated, concentration of the ions raised to the power of the coefficient in the balanced equation. And the concentrations we would plug in are not necessarily saturated solution values. So we've got a couple of scenarios. If Q, which is the product of the ion concentrations that were given, is less than Ksp, we don't have enough ions in the solution to make a saturated solution. Therefore, we're not going to have a precipitate. We don't even have a saturated solution, so there isn't excess that could sink to the bottom as a precipitate. If Q is bigger than K, it means that the product of the ions is greater than the maximum that the solution can hold. That means the excess ions will precipitate out. So we'll have a precipitate forming if Q is greater than K. And then the last scenario is if Q is equal to K, and if we calculate Q from a set of information we're given in a question and it equals the solubility product, then we have a saturated solution and we would have no precipitate, but any more that's added to that solution would precipitate. So let's look at an example. We're going to mix two solutions together in this question. We've got 20 milliliters of 4.5 times 10 to the minus 3 molar silver nitrate. And we're going to mix it with 10 milliliters of 7.5 times 10 to the minus 2 molar sodium bromate. Will a precipitate form? And it tells us that the precipitate that might form is silver bromate, and it gives us the Ksp value. All right, so we're going to look at an equilibrium between silver bromate and ions in solution. So let's look for the silver ions first. Okay, the silver ions are going to come from this first solution. We're given the molarity and we're given the volume. We can calculate the moles. Molarity times volume equals moles. So 4.5 times 10 to the minus 3 times 0.0200, we're just converting milliliters to liters, tells us that we've got 9.0 times 10 to the minus 5 moles of silver ions in the solution when our two solutions mix together. So we want to do the same thing for the bromate ions. They come from our sodium bromate solution. So from what I did, mirror what I did, we've got 10 milliliters and 7.5 times 10 to the minus 2 molar. Calculate the moles of silver bromide. And after you have that, put it into the chat. You're going to do the same thing that we did for the silver ion for the bromate ion. So we're going to take 7.5 times 10 to the minus 2. That's our molarity times, oh, that's not the right number. Oh, no, it is. Sorry. 10 milliliters. We're going to convert that to liters. And we're going to get 7.5 times 10 to the minus 4 moles. Agreed. Good. All right. Now, what are we going to do with that? Well, we need to calculate molarities. To do that, we're going to take the moles and divide it by the volume. So for the silver ion, our moles are 9.0 times 10 to the minus 5. The volume is the total of the 20 milliliters plus the 10 milliliters. So 20 milliliters plus 10 milliliters gives us 30 milliliters. We're going to convert that to liters. Moles per liter gives us the molarity. So the molarity of the silver ion in this mixture of two solutions becomes 3.0 times 10 to the minus 3. So do the same thing for the bromate ion. Calculate what the molarity of the bromate ion is. Moles per liter. Agreed. Now I just wrote it in scientific notation. It's okay that it's not. So 7.5 times 10 to the minus 4 divided by the total volume, which is 0.0300. So the molarity of the bromate ion is 2.5 times 10 to the minus 2. All right. We want to now write our K expression, or actually we're going to use Q, and use these molarities to calculate Q. So the concentration of silver ions times the concentration of bromate ions in the solution is going to give us Q. So take the molarity for the silver ion and the molarity for the bromate ion, plug them into our Q expression and calculate what Q would be. So 3.0 times 10 to the minus 3 times 2.5 times 10 to the minus 2 tells us that Q, the product of the ions that are in the solution, is 7.5 times 10 to the minus 5. That's our Q value. All right, now the last thing. Let's compare it to K and see whether a precipitate forms. Well, K is the maximum product of those ions in solution. This is the maximum value. Is Q bigger or smaller than K? Bigger. Good. So if Q is bigger than K, that means we have too much ion in solution. Which way would this equilibrium shift if we have too many ions in the solution, right or left? Left. Are we going to form a precipitate? Yes. Yeah. Okay. So in these kinds of questions, we're taking two solutions and we're mixing them together, and we want to find out whether we have too much ion in the solution. And if we do, then a precipitate's going to form. All right. So let's look at this one. Okay, consider the following. So we've got this equilibrium here. If the concentration of silver ions at a certain point is 6.3 times 10 to the minus 5, and KSP equals 9.1 times 10 to the minus 14, will a precipitate form? kind of the same concept, a little different wording. We're not taking two solutions this time, just one solution. So what we want to do is we want to write our Q expression. Now, silver ions are going to be 3x. Phosphate ions are going to be 1x. We're given the silver ion is 6.3 times 10 to the minus 5. So we're given 3x. We want to calculate the phosphate ion, which would be x. Plug those numbers into our Q expression, and then compare that value to the KSP expression. All right. So here's our dissociation. We've got our silver phosphate dissolving to form our ions. We've got 3 times the silver ions as the phosphate ion. So figure out what the phosphate ion would be. It gives you the silver ion. The key to that is silver equals 3x. And 3x equals 6.3 times 10 to the minus 5. Agreed. So you are dividing by 3 to solve for x, which gives you your phosphate. I totally agree. Okay, so our silver ion is 6.3 times 10 to the minus 5. That means our phosphate ion is 2.1 times 10 to the minus 5. All right. Here's our Q expression. Silver ions cubed, okay, silver ions cubed, times phosphate ions. Okay, here's your silver ion, so plug that in here, cube it. Here's your phosphate ion, plug it in here, calculate Q, compare it to K, and decide whether or not a precipitate would be forming. Okay, so 6.3 times 10 to the minus 5 cubed times 2.1 times 10 to the minus 5. Calculate that value, compare it to K. All right, so for Q, I'm getting 5.3 times 10 to the minus 18. Okay, is this number bigger or smaller than K? Is 5.3 times 10 to the minus 18 bigger or smaller than K? It's smaller. Good. So are we going to form a precipitate? No. Good. This is the maximum product. Okay. Above this number, we form a precipitate. Below this number, we don't. We have an unsaturated solution.